right, for normal distribution, here's the part that's different. In the past, we've always had one phone call, two phone calls, three phone calls. We've never had like 1.2 phone calls, right? But this distribution will allow us continuous data. Can you underline that, please? And it's influenced by the normal curve, which is the bell-shaped curve that you're familiar with. But there's something you probably weren't told that you really, really need to know. And that is here's the equation. Have you seen this? 1 over the square root of 2 pi e to the negative z squared over 2. Have you ever seen that before? Never seen that before? This is the normal distribution. You're going to see this in a little bit, but it's a surprise, so I'm not going to tell you about the surprise. But this is f of z. F of z is the same as z, or is it x or y? F of anything. This is like your y value, right? So here's what I want to know. What do the y values mean on a bell-shaped curve? Turn to your neighbor real quick. What do the y values mean? I want this in your notes. Anybody know? Anybody know? Anybody guess? What do the y values mean? No. Nope. 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 They mean absolutely nothing, and I want that in your notes. The y values mean absolutely nothing. What's key to the normal distribution is not the y value, or not the y values. The part that's important are the areas under the curve. Because what's the area under a curve? What's the area under the entire bell-shaped curve? What does it have to be? 1. So, yeah. Well, no. I'm saying as far as representing it with probability or standard deviation, it does mean it helps us to get the area, but it doesn't represent probability. Y values do not represent probability. The area does. The area is the probability. So I just want to get, sometimes we do things and we don't know what we're doing. Yeah, I can do normal distributions, but you don't know what anything means. You just know how to do the problems. And I hate that. Y values don't mean anything in the distribution, but the areas do. And the areas always start from negative infinity to some value x of that f of z, dz. And we'll actually take these integrals, and I can't wait, but we're not going to do it right now. The mean, the middle is 0. The standard deviation is 1. Those are the breakdowns that we're going to look at areas. 4 areas, I want you to kind of memorize these, not for me, but it's just a super powerful thing to be able to do, is that if you split to 1 standard deviation, -1, this area is 0.34. And it's symmetrical, so this is 0.34. If you go another one, it's about 13.5, about 0.135. And the reason that's significant is this is 68%. From -1 to 1, that's about 68%. That's a big chunk of it. If you go from -2 to 2, that's an even bigger chunk. That's about 95%. And then when you go from -3 to 3, it's almost 100. Not quite, but it's pretty close. So this tails off pretty quick, converges pretty quickly. Standard deviations down here are my z values. Those are the z values. All right, so that's kind of the overview of this. And you can do problems really easily. This summary is helpful. To find the standard deviation, find the x value that you care about, subtract the mean. This is the data. This is the mean. And this is the standard deviation. And sometimes you'll be asked to find these. Then this here, z value, is how many standard deviations from mean that you are. And we have normal CDF, normal PDF, inverse norm are the three that we'll have. And I think probably the best way to do this is to zip on to an example. Manufacturer produces engines that hold oil. The mean, mu, is 118 centimeters. The standard deviation is going to be 0.3. Find the percentage of rejected rods that are 118 centimeters and over. So draw a little bell-shaped curve real quick. The middle is the mean, 118. If I went 118.3, that's one standard deviation, 34%. If I went back 0.3, it'd be 117.7. That would be 34%. So you can see that if we're at 118.37, we're sitting out here and over. Does that make sense? 118.37. So what would you estimate this to be? If this is 34%, there's only about 16% left. So I would guess it'd be, maybe 15 or 0.1415. Isn't that what you'd expect? Not too much. So we're going to go right to the calculator here. Normal CDF. And that's going to be, you start with your low, go to the high. So the low is going to be 118.37. My high is going to be what? I'd be interested in what you think. Infinity. But we don't write infinity. Just write something way, way, way big like 1,000. That's going to be more than 5 standard deviations. You got it covered. Oh, no. Then you have to put your mean and then your standard deviation, which was 118, 0.3. And so when you calculate that, somebody calculate that for me. What's that? So it was about 11%, kind of what I estimated, less than 16. And that's all you do. Here it's going to be the low is this one, the high is this one, mean, standard deviation, no problem. If you don't have a z value, when you're doing these things, x minus mu, if you don't have this, you need to do an inverse norm we'll look at tomorrow. But for the homework, go ahead and do these problems that are assigned, and I think you'll be great. Only use your calculator.